Just really, really excited to introduce Zulfi Alam. He's our corporate vice president for quantum computing. He's been at Microsoft for almost 25 years, I believe, and led many, many tremendous projects. You may have seen the announcement just very recently around the Majorana 1 topological supercomputing chip. An absolutely amazing effort, joint effort led by Zulfi. He reached out to us because he wanted to talk about some of the work he's been doing in materials in the quantum computing program and how that might be applicable to nuclear fusion. So with that,
thank you so much. Thank you all for super appreciate it for this opportunity to speak to you all. So I know nothing about fusion, so it's a little bit odd, but I do know a lot about quantum computing. And the thing is, quantum computers will be here, and the first instantiation be publicly announced by the end of this calendar year. It'll be a smallish machine, say 50 logical qubits. And the thing is, we are trying to figure out what the right applications for these machines are, because it's not easy finding the right application. It turns out chemistry and materials is sort of a signature area where quantum machines will add a lot of value. And so we reached out to some of the startups in the fusion space, trying to understand what their material needs were. And we kind of came to interesting realization, which was sort of one of the key things that they told us they would like to solve for is this notion of diffusion of hydrogen across within their reactors and also within the piping that actually gets the material to the reactors. Turns out, apparently, tritium and deuterium are really expensive and really hard to get by, and there's not a lot of it in these labs. And so any loss that we can minimize is appreciated. And it turns out that there's no easy material that can help solve that problem. Seems like the hydrogen isotopes just diffuse quite rapidly through the material set. The reaction chamber is compromised after usage. And they would love to figure out a mechanism of being able to handle these losses as best as they can. And we in the quantum domain have been messing around with a bunch of different exotic materials and trying to figure out how to protect them. And turns out that silicon nitride is a fantastic barrier. We mostly use it to prevent hydrogen and or vapor from getting into our devices. So we've been working very, very closely with this material set for the last 5 or 6 years. And it turns out, based on looking at some of the literature, that it is also known to be a good barrier for things like deuterium and tritium. So the key issue turns out to be, fine, we can have this material, seems like it's a good material, but how do we bind it to the reaction chamber? And that is not an easy problem to solve for. And so we've been looking at investigating what sort of intermediate layers do we need or can we come by that will help bind these devices better. And I think Chichan is here in the audience, so thank you for that. But there are folks on the team who actually know how to do this and know how to do this really, really well. So we recently, maybe a year and a half ago, showcased electrolyte. And essentially, the notion was we were able to compute in about 80 hours what material scientists would have taken many, many years to figure out, just at least a starting point. Now, it turns out actually synthesizing and fabricating the material is much harder. but the initial getting to the right design point is super straightforward. And essentially, we looked at 32 million candidates, brought it down to about 18. Turns out the candidate that we selected had 70% less lithium than what is existing in the marketplace, and it was a fantastic proof point of what can be done with using the AI systems that we have developed in-house. And what we've been messing around right now in the labs is trying to figure out if we can use the same approach to come up with a better intermediate layer for binding the silicon nitride layers, or thin films of silicon nitride, to the reactor chamber. So looking at millions of materials, using fast screening AI to look for thermal expansion, mechanical properties, adhesion properties, cycling that down to about 500 or so candidates, where we are looking at DFT, essentially using HPC to figure out and MD simulations, how we get down to the next 50-ish or so candidates, where essentially our subject matter experts can look at the 50 or so manually. We are not there yet. AI models are not good enough to essentially come up to the right answer, but they get us pretty close. And what we are essentially showcasing is, and this is an actual SCM of sort of the films that we are synthesizing in the lab right now. If you look at polycrystalline layers, they're supposed to be good, but just looking at the SCM, the grain boundaries are wide enough that they are not good barriers. And if you look at this amorphous layer of silicon nitride, it's beautiful. You sort of zoom out and it's amorphous, but it's got very, very good long-range properties. And we are very excited that once we figure out the right underlying binding structure, we can come up with a stack that will work for our potential customers. Looks like we have a target. It's silicon tungsten carbide. Looks like it's very, very promising. Not done yet, but nonetheless, what we feel is like we are onto something here which is going to yield some fantastic benefits. And how this all sort of fits into the whole quantum story is the funnel that we showcase is leaky. We'll have potential good targets that will get through the funnel because our ability to simulate using HPC is good, but not excellent. And I think the mission right now with the quantum machine is to start building out a database of materials such that when we run the AI tool on that database, we'll just get better answers. And our expectation is that with the first instantiation of this 50 logical qubit machine, our ability to predict the sort of problem that I just discussed in the previous slide will become infinitely more accurate. And the fundamental promise that we are making to our community is the predictions have to be first time right. That's a tall promise, but that's what we're going to prove out in the next 3 or 4 years. Then the prediction is not enough. AI tools will actually do a fantastic job of prediction once you have a good data set. The more interesting point is getting the right recipe. How do you synthesize the material? We talked about this example of the battery earlier. It took us 80 hours to simulate the right answer, and it's taken us a year and a half to productize it, and we're still not done. So the cycle of actually synthesizing something is much, much more painful than coming up with the initial answer in the lab. And so our goal is to be able to get to an efficient synthesis by having the exact recipe defined up front. And then finally, things that really, really annoy product people is the life testing and being able to predict how this material will perform over time. And I think the promise of the quantum machine is that for a class of materials, especially in the field of chemistry and material science, we'll be able to do a very, very good job. And the example of the fusion reactor is a good one because essentially it will, when we think about material and how it corrodes, it's about how it's enabling the environmental molecules to get through the structure. And we can predict that to a large degree once you do have fantastic models. So that's what our journey is. Short talk, 5 minutes, but wanted to make sure that we put ourselves out there for the fusion community, that there's goodness happening, and we'll be delighted to partner with you all in the coming months and years. So thank you for that.